Well, welcome everyone. I hope everybody will be here by the end of the talk. That actually never happens to me. I'm starting on the split second instead of the usual 5 minutes late, so that would be an unusual speech. So, welcome once again. Let me introduce myself. My name is Alex, and I'm CTO and co-founder of MammothDB. I have way too much experience in various shades of business intelligence, data warehousing, and analytics, more than I'm happy to admit to. Most of my career I've been translating between business and IT, who typically don't want to talk to each other. So I'm the man in the middle, making sure they talk to each other. And currently, I perceive myself as a nerd who is working on making scale data infrastructure practical, as opposed to something with thousands of servers that you can't really use in your small company. Okay. So this is how this talk will proceed. I mean, we'll first look at the type of problem we're trying to solve, and then I'll be talking about how we approached it. We'll cover the database architecture, which is our flagship product. We'll touch a bit about on scalability issues that we face with our database architecture. Then we'll talk about how we in particular have approached delivering a reporting and analytics service to an end client via web interface. And I have like a couple of sections on lessons learned. My objective for this talk is not really to teach you how to use MammothDB. We can do that afterwards. Rather than that, I like to share what we have hit when we have been building this particular product, because I think it may be relevant to your experience if you're at any point faced with having to build a reporting and analytics interface for your clients. A lot of the issues that we've hit, probably you hit them too, provided that your client base is big enough and your data is big enough. Okay. So, I mean, the use case that we have approached is providing enterprise analytics as a service. And really the types of clients that our service is serving are clients that have some sort of platform for delivering services that is doing the transactional part of the service, but they think it would be valuable to their clients to have an analytics interface, and they think that can be sold as a service. And I can give you an example with a loyalty card management client. These guys are based in UK. And what they do is loyalty programs for small shops and restaurants and universities and a number of other typically very small clients. And the way they do it, they have an application that does the loyalty card management. It tracks points, it tracks awards, anything that you need in order to use a loyalty card. However, when they came to us, they provided literally nothing to their clients in terms of reporting. Whereas today they're able to get a new client, subscribe them to their loyalty card service, and then provide an interface through which they can track performance of their loyalty card programs. So, I mean, this is more than one instance where it's a client that does a platform that doesn't have analytics and wants to have analytics. And the reason I'm saying enterprise is that another picture we typically see is that at a client like that, there would not be one system that is serving the whole business. There would be a multitude of systems, and they typically wouldn't be the latest and greatest in technology. They would be legacy systems doing relational databases. So it's really, we're not looking at a very smooth end-to-end environment. And I'll take a little diversion and ask the audience a bit. Have you guys ever done, okay, let's try to rephrase it differently. Yes, anyone here never done an automotive comparison, like talking about software as if it were cars? Nobody? Oh, there's one. Okay, you have to hear that. But yeah, I like automotive analogies. So I'll give you my very limited viewpoint about analytics. To me, analytics is a lot like the fancy dashboard that you see on a car. It's not essential to how you drive the car. It's there to make sure that you can plan reasonably ahead, so that you won't run out of gas and you won't be breaking the speed limits. It may improve your driving a bit, especially like if you're tracking your fuel consumption and driving style, but it will not turn you into a radically different driver. I mean, I know nowadays when we talk about analytics, typically we expect to dig some great value from that, but in reality, I mean, a business is very much like a car. These controls are absolutely necessary, but they're not what makes the business run. They just support decision making. They support you they support you driving along a smooth road as opposed to running out of gas midway. And sure, there are businesses for whom data and analytics is the core. That's how they make money, but these are not the majority of businesses. So our very limited view of what analytics is I mean, the dashboard on a car. And well, to illustrate where we're going, essentially this is the kind of interface that we're trying to build easily. Let me start. I recorded it. So what you typically do is you go look at the report, then choose another reporting area as a user, then drill down into your data until you get to the level of detail that you require. Then perhaps choose another reporting area where you want to parameterize and select this report to run, say, for a specific country, Germany in this case. Then navigate from one report to the detailed data. This is what a typical user typically does on a reporting application day to day. They may also want to have a more interactive interface where they really move their mouse over the screen and see the impact of their actions, parameterize it a bit. See interactively what's going on. Another thing they may want to do that you don't typically see in web applications is massage your data directly in a tool that you're familiar with, like Excel, where you open what we call an Excel report, which connects directly to a pivot table server, and it lets you play with your data through a familiar pivot table interface. And so you can do things like drag and drop of different fields, sorting, and selection of filters. Also stuff like search and replace. This is pretty standard Excel functionality that every business user knows and is excited about. The people who do reports actually find that sexy. I don't know how that happened. Okay, let's wait for the Excel report to finish. Okay, and there we go. That's the kind of interactive stuff that you can do with your data. And what's going on here, it's really talking to our backend. There's no data sitting on the Excel worksheet, and it's a lot of data sitting behind the Excel sheet. Okay, so what made this possible is both of our product lines. We have two product lines at MammothDB. One is a database engine made specifically for analytics, and the other one is called MammothDB Storm, and it's a cloud platform for running applications like the one that you just saw. And yeah, I can almost hear like people thinking, oh no, not another database management system. Why are you doing that to us? And I can almost hear people thinking, why didn't you do MongoDB or Cassandra? And the reason for that is because we have certain architectural goals. And the number one reason that motivated building yet another DBMS was to have something that would be affordable when the data gets a bit bigger. And let me tell you a little story about our past lives. We used to be business intelligence consultants building end-to-end systems like the one you saw. And more than on a single occasion, we got turned down by a client when they saw like a 7-digit bill that we presented to them. And guess what? That 7-digit bill had about 1/3 of the total cost in terms of our implementation effort, actually bringing the whole thing together, analyzing their requirements, making sure their data is aligned and reportable. And the other 2/3 were hardware and database licenses. And I'm talking about numbers in the 700,000 to 800,000 euro. And that's just to get you started. I mean, you haven't, at this point, after spending so much money, you haven't still written a single line of code. The client hasn't seen any report. So we kind of thought, can we, well, take one zero off of that number and still make it possible? And that's how the whole idea of Mammoth was born. So what we wanted of the tool that we were going to build is that it's pretty standard. It can talk to all those wonderful tools that are out there in the wild. We wanted it to be very specific to enterprise data systems. We didn't care much about non-structured data because, well, when you go to enterprise clients, the majority of what you find is legacy systems from the old times when everything was relational, or the old times before that. Then we also wanted to be able to give our client an opportunity to share a single infrastructure among multiple tenants, so that the cost that each of these tenants is facing is part of the whole cost of the hardware. And we wanted to run it ourselves as a cloud infrastructure to provide that sort of application as a service. And the final architectural goals we had is that if we approach building a BI application like a standard data warehouse, we could use the same methodologies and tools. which pretty much meant we were going to stay with relational structured data. We were going to speak SQL and provide a standard interface. What we came up with was this kind of architecture. So the key decision we took was scale out on multiple nodes in a standard cluster system where every one of these guys who are doing the work, they are running on commodity hardware in a commodity network. Actually, I'm working on a project to make this thing run on a Raspberry Pi. So it really doesn't need a lot of computing power. Of course, the Raspberry Pi Mammoth will be shitty when compared to your ordinary single server, but it still demonstrates the concept. So something that's very specific of our architecture is that we are storing our data on a relational database sitting on each of the worker nodes and doing most of the querying against that relational database. This is, in our production environments, this is a columnar data store from a third-party vendor, open source, of course. And actually, we're finding the columnar organization pretty good for analytical applications where you have infrequent writes and a lot of reads. Then we have a couple of query engines. These guys are redundant, so that if one fails, the other will take over its functions. That are doing the client interface. They provide a MySQL interface to any sort of client, ETL, or reporting application. And actually, the client doesn't know it's MammothDB under the hood. It thinks it's stock MySQL. So any reporting tool that already has been integrated with MySQL can be used transparently. So in this architecture, we have two key data flows. One is to get the data in. And the way you do that, you provide standard data, a standard data source like a CSV, do a load data statement in MySQL, or an insert statement that would also get you the data from already existing tables. And the query engine will take that data and distribute it to the worker nodes. Now there are two ways it can do that. It can either take a large table and cut it into pieces and then place each piece on one of the nodes. We call that partitioning. Other people call it sharding. It's a pretty standard way to scale out in the database world. But we also have a second option, which is to replicate a table. Whenever you have a small lookup table or a table that's going to appear a lot in joins and is relatively small compared to the big table sizes, it's a good idea to have a copy of it sit on the worker node. And in a second, you'll see why it is a good idea. When we get to our query data flow. So what happens during a query is that, again, the query engine that talks to the client application intercepts the SQL, it does a rewrite, and then it executes the rewritten SQL on each of the workers, then aggregates the results and returns them back to the client. And the reason it was significant to have replicated tables is that if the data that you needed for a join wasn't sitting on the same node, you'd have to move it over the network. The more efficient implementation is to just have a copy of the data that you're going to use for lookups and just execute it on the worker node without any data movement during the query. So at this point, I mean, there is a data schema that's very close to this model of working, having small tables for lookups and large tables for large tables that contain measurements. It's called the star schema, and we use that. I mean, as the assumption, because this is the standard way to build data warehousing applications. We use that as the assumption that this is how the data will be structured if we are looking for good performance on this infrastructure. So let me touch a bit upon why do we need to do the rewrite. Essentially, you cannot, there are SQL statements that you cannot just run on the worker nodes and then aggregate their results. You need to rewrite them so that you can make sure that the aggregation at the end works as it is intended. And average is a good example of that, because what you will get on the worker node, if you just run the select average, would be a bunch of averages that you have to consolidate after that and get a correct average, which there is no way to do that if you average the averages. So what you need to do in that case is you need to break the average function into a sum and a count, and then divide the sum of the sums by the sum of the counts as a final step on the aggregation. So another example of where you need to rewrite a query is when you want to do select any aggregate function over a distinct subset of a column. Then what you will do in the cluster is you'd first perform a select distinct operation on all involved columns. Then you will only do the sum of the distinct values as a second step once you've aggregated all distinct values. Am I making sense so far? Okay. So, well, the star schema that I briefly described, that's our totally ideal use case. Did I mention that we were targeting a standard data warehouse built methodology as a target for our database server? I think I did. Well, that's what comes out of the standard data warehouse build technology. Usually you have a number of transformations of your data, and you have a reporting area at the end that is structured in this way. What this structure gives you, it gives you a way to describe measurements, which is the fact table, by any number of attributes, and it gives you a very simple way to manage the attributes depending on whether, for example, you want to update a value and then see the history in the report being updated, or you want to keep the historical value of the attribute. That's fairly easy to do. And if you want to join, typically a fact table would be representing one business area, for example, invoicing. If you want to report on facts related to invoicing and, for example, CRM, the way you do that is through a shared dimension. You make an aggregation on the CRM facts, say visits to the customer, on the customer, and say date, and then you perform similar aggregation on the sales and the customer and the date, and then you join the results of the aggregations to one another to get a figure side by side for the sales and the visits. And that organization gives you a lot of flexibility in terms of adding new stuff to the schema. You just need to add more fact tables. You need to make sure they adhere to the same dimensions. Okay, so as I mentioned during the query, what will happen normally is that the query will be fired in parallel to all nodes. This, however, even though that this is very good for scaling when the data gets large, because we process our data in parallel, that's one thing that's not very neat, which is it takes up, say, one CPU per server to do just that query. I'm assuming that there is a single core per query per server relationship. So one query runs in a single thread. And what will happen when you run the query in parallel on all the servers to process their local piece of data is that these guys will be busy and they won't be available for any other queries. And that way, essentially, you're taking a horizontal slice of the infrastructure to do just one job, which is limiting your concurrency quite a lot. Essentially, you can run only a number of those. Say if you're running eight CPU servers, there will be 8 concurrent queries that can run in this fashion, which is not a lot. So if you want to scale on a second potential objective, which is the number of concurrent users, you have to do something different. What we've come up in this case is to advise you to first find the natural partition of your users. Typically, there is such a partition, and make sure that, for example, user ID. I mean, that's the most obvious one. That when they're running their own queries, they're only hitting one spot on one server. So they don't need to run the query across the whole architecture. And this gives you access to as many CPUs at any one time as there are in the cluster. So essentially, on one hand, you can serve the individual users, individual objects that have been partitioned by running their queries directly to the corresponding server. But you can also do aggregations and ETL jobs when you need a lot more processing power and are going over a much larger data set that's not filtered by a user ID. For example, if you're doing an aggregation over the whole user population. And we've found that actually if you reserve some slots for your big queries and leave the rest for this type of access as directly to the server, that has a minimal impact on the overall performance. You can still run a large number of users smoothly here. And this is how it works. I mean, this particular optimization, this is how it works. You first partition the table on a natural partition key that's aligned with the way your users are accessing the database. And then whenever you get a query that has a condition on that partition key, it will be sent directly to the worker node that holds that we know holds the data for that partition. In the other case where we don't have such a condition, we would be running the SQL in parallel on all nodes. Okay, from these are the lessons that we've learned, we think, while building this tool. Overall, we've gone for the good enough principle, and in many cases, in technology selection, people, just because it's so expensive and it's something that you expect to be using over a number of years, they go for high-end solutions that they expect to be using. They take on much more functionality than they really need and end up using just the part that they need. Our view is that we go for what's good enough. what will do the particular job and will be there for a couple of years. So far that's been pretty successful. Actually, if you don't associate a purchase of a large layout with that, most business people accept that principle. I mean, good enough, we'll do the job, let's do it, rather than go to the board, approve a large budget, and hope we might be able to do it someday. Second thing that when choosing your backend architecture, I think is pretty critical, is get to know what the specific tools that you're looking at can do. Because, well, many tools will claim that there are things they're not. For example, I get always the question of how are you similar to Mongo, and how are you similar to, say, Spark SQL? And the answer to those is a very complicated technical discussion, but the short version is that they were built for a completely different use case. And trying to fit them into a universal use case usually ends up in redoing your architecture. So before making that decision based on marketing materials, we'll learn a lot about how your tools work in reality, because that gives you a baseline on how you're going to use it. And that's really like the point of ensure the way you plan to build your solution actually addresses your problem. For example, if you try to take a database that does table locking in a very high concurrency scenario, that will not be a good decision. So make sure you've played around, you've prototyped, you know high concurrency would be your biggest issue, and you have tested that database with the expected usage. And I mean, I cannot overstress prototyping. Whenever you select a technology, just build a small version of what you're trying to do. And scalability is one of those things that when you get to the point of having to deploy, it's too late. I mean, you cannot go back and replace the Cassandra that doesn't perform well on searches with something else, because you have to rewrite the whole application. The challenges that we've seen in building this tool is, I mean, mostly two. One is supplying all the enterprise tooling for backups, restores, high availability, stuff that any sysadmin will ask about. This doesn't come out of the box with the third-party tools that we've used in our architecture. We had to build them, and they're still in progress. It's not like a fully completed challenge. And the other thing is running efficiently a support for any database schema, like joining large tables to one another that are not partitioned on the same key requires moving those data through a network. And because we're using commodity and are very particular on using commodity hardware, the effect of that is, I mean, if you want to join tables that are not partitioned, the design time to be joined, that costs a lot of time. So that's something that, I mean, until like 40 gigabit networks become a commodity, I don't see that being resolved. There are other tools out there that use fiber channel and other like high-end communication technologies that solve it, but it's not our goal. That said, I think if you're mindful of how your data is distributed, you're good enough, the good enough principle with Mammoth as well. So let's talk about the next thing that we've done is, well, build a whole end-to-end platform for delivering BI services on top of that. So the challenges that we're trying to address with that, these are challenges to the customer, is having a try before you buy opportunity, because in enterprise analytics, oftentimes you have to get board approval to just try something, which is difficult because the money involved is a lot. Then the next challenge is the cost, effort, and timeline to just get started with regular tools are just too much. Then if you take the regular tools, you have a lot of activities to just integrate them and have them talk to one another. Whereas if you could focus on just what's adding value, getting the data in, aligning the data so that it can be reported on, actually, I mean, if you can just focus on that, the timeline, cost, and effort will be much smaller. And finally, final challenge is provide smooth transition from a proof of concept that you build quickly for trial purposes to a production system. And the environment in which this is happening at the client is typically the data sources are enterprise. They're coming from multiple places and they're not exactly aligned. For example, a customer in your billing system doesn't correspond one-to-one to a customer in your switch. And I guess like everybody can point to specific problems like that in their own environment. Like the moment you have two systems that are supposed to talk to each other, there are people trying to bastardize the interface and do something for legitimate business purposes that, however, it doesn't leave the data aligned. And ultimately what we see at every client is that they started to do something and they have lots of Excel worksheets and databases sitting on a personal PC somewhere. A lot of efforts and attempts have been made to build analytics, but it's never ended into a single consistent end-to-end system. And to address that, I mean, we built a run platform that essentially follows standard data warehousing methodology. We expect data to be delivered to a file system, then we have some data integration tools. They load the data and process it into the distributed database. And then there are a number of channels through which the data is delivered to the client. And the structure that we work, I mean, our central component is the distributed database. The typical structure of data as it moves through the various stages of processing is we start out with a staging area where we load the source data one-to-one. Then we do transformations to get this data aligned and make it into a consistent state. Especially when it comes to reference data like the client ID that I just mentioned. The role of this target area is to have tables where the client ID is properly mapped in each system so that it means the same thing in both systems where the data is coming from. And then we have a reporting area at the final step that is a dimensional model, the star schema I referred to earlier. So this is directly used for one-to-one by the reporting interfaces further on. Okay, so this is how we deliver the final interface. We have at the bottom of it, on the reporting side, we have the distributed database with the reporting area in dimensional format. And we're actually running SQL Server analysis services on top of that. which does a number of things. I mean, firstly, it provides a unified data model that the users can view and manipulate. This is what you see as fields in the pivot table in Excel. It provides a high-level caching of these aggregated queries. So instead of an aggregated top-level query that runs through the whole organization for a whole lot of history, every time such a query is accessed by a user, this is cached in SQL Server Analysis Services. And it also provides a native interface to the Excel pivot tables. Then on top of SQL Server Analysis Services, we have reporting services or Tableau, whose role is to help in authoring reports so that not only programmers but also business users can create reports. And they also render the reports once they are authored and published. On top of that, we have a web portal that handles the management of users and their rights. We have a report manager. It also handles report management, saying which reports is visible by whom, doing publishing of reports. It handles the delivery of reports through a proxy, so for each call that a client browser will make, actually that will be proxied, verified against the security service, and then rendered by one of these guys. It provides an XML endpoints for people to connect using Excel. And it also provides a REST API endpoint for something that's not yet in production, but it's upcoming. It's a data delivery API where people can provide data sources for their downstream applications, and it's an integration point if you, for example, want to do interactive reports with one of the JavaScript-based reporting mechanisms, for example, high charts. Okay, and I mentioned a key, actually a very key component of our delivery to the client, because we are running multi-tenant, is to be able to identify a client and make sure that client accesses only data that they can view. So we have implemented a data security mechanism on top of that. It starts with an external ID between the web portal and the client application, be it Excel or a web browser, which client ID is then translated to an internal ID. And actually this internal ID never gets outside of our network. The user management module is the one that makes sure that any changes to that internal ID, as well as any changes to the permissions that the user has, are distributed to an Active Directory infrastructure. And from that point on, all these tools are using integrated authentication to apply that security. So the stuff that makes it to the reports proxy uses the fact that all these tools can talk to an AD server and verify what the user can do. That's always the internal user, never the external user. And finally, I mean, in the data delivery API that's upcoming, actually the service will make sure that the SQL or MDX that this data delivery API will be issuing will have an additional workload to narrow down just to what the user can see. So it's really whatever the user does, there will be an additional workloads filtering data that they can see and filtering out data that they cannot. And actually, our vision of the data delivery API is for downstream integration. That's how it works. I mean, you create it with a simple call containing like an endpoint name, is it a SQL or an MDX, and the select statement that contains parameters. And then once that is published, it can be accessed by downstream applications by just calling a REST API and providing the parameters. The security parameters are passed by the web portal always, independent of the fact that they don't appear in the endpoint. And that's how we narrow down the security. And then the few lessons learned from, this service architecture is number one, again, the good enough principle. These are not the shiniest tools, but most users view them as a big step forward, because before that they have nothing or a spread mart of Excels across the organization, and it's very easy for them to make that first step, make a prototype, and see their data being reported on consistently. Second, big takeaway is users love the tools that they already know. It's difficult to teach them something new. And actually, there are great tools out there integrating with one of them rather than building your own. In most cases, works and is quicker and cheaper. Final one is integration is a tough exercise. A lot of effort goes into that, so don't make your client do it. Our platform does it for them. And the challenges that we still face with this platform is we haven't figured out how to give people a way to alter reports through the web service, web interface, and we haven't figured out a secure way to give direct database access to users. And I think my time is up, so thanks for not falling asleep.